Welcome back, 10th graders. Today we're taking on the highest yield chapter in your chemistry syllabus, carbon and its compounds. By the end of this session, you'll be able to break down carbon's unique bonding traits, follow the IUPAC rules to name organic molecules, memorize the 4 core chemical reactions, and see exactly how soap breaks down dirt at a molecular level. Grab a notebook and a pen. Draw a line down the middle and across the center of a blank page to divide it into 4 distinct quadrants. We're going to build your master study guide right now, step by step. Organizing the chapter into these 4 quadrants converts a long list of properties and names into a single, logical structure. Once we fill this page, you'll have a focused reference guide to use for the active testing we'll do at the end of the video. Let's fill in Quadrant 1, the bonding dilemma. Carbon has an atomic number of 6. That means it has 2 electrons in its inner shell and exactly 4 valence electrons in its outermost shell. To become chemically stable, it needs a full outer shell of 8. But if it tries to gain 4 extra electrons to form a C4- anion, it fails. As you can see in this model, a nucleus with only 6 protons does not have the attractive force to hold on to 10 orbiting electrons. It also can't take the opposite route. Losing its 4 outer electrons to form a C4+ cation requires a massive amount of energy to overcome the pull of the nucleus, leaving behind an unstable state with just 2 electrons. Since it can't gain or lose, carbon shares. It overlaps its outer shell with other atoms, so the electrons belong to both. Here, carbon shares its 4 valence electrons with 4 hydrogen atoms, locking together to form a stable methane molecule. This ability to bond with 4 other atoms is called tetravalency. Combine that with catenation, carbon's ability to form long, stable chains and rings with itself, and you have the mechanism that allows carbon to construct millions of different compounds. Moving to Quadrant 2, the hydrocarbon divide. Hydrocarbons are compounds made of just carbon and hydrogen, and they split into 2 categories based on how their carbon atoms link together. On the left side of this table, we have saturated hydrocarbons, or alkanes. Notice the structure of ethene here. Every carbon atom is connected by a single bond. Because all the valencies are fully satisfied, these molecules are generally unreactive. On the right side are unsaturated hydrocarbons. Look at ethene with its double bond and ethyne with its triple bond. These multiple bonds are areas of high electron density, which makes unsaturated molecules more reactive than saturated ones. We see the results of that reactivity in this photo. The intense heat cutting through metal is produced by burning ethine, an efficient industrial fuel. Identifying whether a molecule is saturated or unsaturated is the first step in predicting how aggressively a chemical will react with other substances. Now for Quadrant 3, the nomenclature rulebook. You can consistently name any organic compound using IUPAC rules by following 4 specific steps. Step 1. Count the carbon atoms. 1 carbon gets the prefix meth, 2 is F, 3 is prop, and 4 is but. Step 2. Check the bonds between those carbons. If they are all single bonds, the suffix is -ane. A double bond gets -ene, and a triple bond gets -ine. Step 3. Identify the functional group. Alcohols end in -ol, aldehydes in -al, ketones in -one, and carboxylic acids in -oic acid. Pay close attention here. Confusing the -al of an aldehyde with the -ol of an alcohol is a common mistake on exams. Step 4. Apply the vowel rule. If your functional group suffix starts with a vowel, drop the final E from your carbon chain name. So a 3-carbon propane chain plus the ketone suffix -one becomes propanone. Mastering these rules allow you to look at a chemical name and accurately visualize its entire molecular structure. Let's fill out the final quadrant, the core 4 reactions. First is combustion. As you can see from this coal, carbon and its compounds burden oxygen to yield carbon dioxide, water, heat, and light. Second is oxidation. By using an oxidizing agent like alkaline potassium permanganate, you can add oxygen to a starting material, converting an alcohol into a carboxylic acid. Third is addition. If you take an unsaturated hydrocarbon, you can add hydrogen atoms to make it saturated. This process requires a catalyst like nickel or palladium to work. Fourth is substitution.
Since saturated hydrocarbons are relatively unreactive, you have to use a reactive element like chlorine. In the presence of sunlight, chlorine replaces the hydrogen atoms on the chain one by one. The governing rule here is simple. Unsaturated molecules use addition to fill their empty bonding slots, while saturated molecules must rely on substitution to react. Let's apply what we know about carbon chains to a daily problem: washing away dirt. Look at this diagram. A soap molecule is built like a tadpole. It has a hydrophilic head that attaches to water, and a long hydrocarbon hydrophobic tail that repel water but attaches easily to oils. When you put soap in water, these molecules cluster. The hydrophobic tails pierce the dirt particle to escape the water, while the hydrophilic heads point outward. This formation is called a micelle. The geometry of the micelle shows how carbon chains can be engineered to trap dirt and wash it away. Your 4-quadrant study guide is complete. Now, let's use it for a rapid mock exam. I'm putting 5 multiple-choice questions on screen. Pause the video and write down your answers using your notes. Next, here are 3 high-order thinking skills questions. Pause again and note down your reasoning. Once you have your answers, check your work against the master answer key pinned at the top of the comments. Scoring an 8 out of 8 shows that your study guide captures the critical high-yield concepts you'll face on test day. Keep this guide for your final revisions, and subscribe for more 10th grade science masterclasses. Keep studying, and I'll see you in the next one.